here are your solutions to review assignment 13. I took a separate piece of paper, write down review assignment number 13, and I actually just sketched what was in the book, so I had space. So here's the first graph. This is the graph of the derivative. Our goal is to think, what could the function look like? So we're going to do a first derivative number line, and it's undefined at 0, and I see it's increasing, it's above, and the second part's above. That means the whole thing is increasing. And then the second number line is the second derivative, and again, our only critical number there is 0, and it's increasing, and then it's decreasing. And this gives me concavity. So that means the whole thing is increasing, concave up, and then concave down. So this is what the function could look like. And then in the middle, we have an asymptote. So we know that there's an asymptote there, and it's concave up, and then concave down. So this is increasing, this is increasing, this is concave up, this is concave down, and there's an asymptote. Let's try the next one. So I'm going to draw a number line. I'm going to say, what are the critical numbers here? So we have -2 as an endpoint, and the other endpoint is over here, 1, 2, 3, 4, 5. We have a critical value here at 2. So this is above, and then we have another critical number at 1, 2, 3. It's above, it's below, and then it's above again. So let's write it so you can see it a little better again. So it goes from -2 to 5. So what am I looking for? It's undefined at 2, and it's equal to 0 at 3. Those are my critical numbers for the first derivative, above and below. So from -2 to 2, it's above. From 2 to 3, it's below. And then 3 to 5, it's above. That means it increases, and then decreases, and then increases again. So right here is going to be a minimum, because it goes down and then up. The second derivative, the critical numbers here are just right here at 2. We don't have any turning points, so this increases and the second part increases. So both sides are concave up. And then we're going to draw a picture of this. So it goes from -2 to 5. So it increases and concave up. So it increases and it's concave up, and that happens all the way to 2. So here we are, I'll put a point there. So it increases and it's concave up. The next part, it's going to decrease and it's concave up. And then at 3, to 5. So this increased and curved up. This continues to decrease but concave up, and then creates a minimum at 3, and then it continues. So this whole thing is concave up with a minimum and holes here at 2 and 3. Let's try the next one. I know it's a little tricky. So where is it equal to 0? At -2 and +2. This whole thing is above. So it's above, above, above. That means the whole thing is increasing. How about concavity? So again, the critical numbers are the turning points, which happen to be at -2, at 0, and at 2. And so this is decreasing, then increasing, then decreasing, and then increasing. So this is concavity, and then we connect all the pieces here. So I'm going to have -2, positive 2, and 0. And then what could a sketch of f look like? So we know the whole thing is increasing. So it increases and is concave down. So it's increasing and it increases the whole time. So increases, concave down. Oops. So, and then at 2, it now is concave up and continues to increase up to 0. So it increases, it increases. Here it's going to continue to increase but be concave down. And then continue to increase and be concave up. So this whole time it's increasing the whole time. It just changes concavity. Concave up, concave down, concave down, concave up. So it goes back and forth. Down, up, increasing the whole time. Done. Number 4. Maybe I'm interpreting what. Use these graphs of the first derivative. Oh, to graph the second derivative. Well, I'm like doing the next step here. I can tell you what I'm doing. It's all good. Do what I'm doing. So number 4, again, I think I misinterpreted the question, but I'm going to just move forward here. What are the critical values here? Just at 0. And this is above and this is below. Here, we have at 0. We have no concavity here because it's not increasing or decreasing. So this one has no concavity at all. So it's not concave up or down because it's not increasing or decreasing. So what does that mean? They're lines, right? It's a line. And so if you think that this is going to increase to 0 and then decrease after 0, like what would that look like? So it increases and then decreases, and then at 0 it is undefined. And there's no concavity for line segments. And it's done. All right, number 9. We're moving on. That's what I wanted you to do. Number 9. At the graph, at the right models a rate. And it gives you a table of values 2 connected to it. Tell what point A represents. So there's point A at 2. So 2. So years beginning from 1990. So 2. So in 1992, how we would start. So in 1992, what happened? The rate of births is, the birth rate is, and it would be in thousands. So that means 3,000 births per year. In that Utah city, but that's what we're looking at. Part B, approximate and integration. Now, when we integrate off a graph, we're finding the area. So we're finding the area from 2 to 6. So from 2 to 6, so if I was going to estimate from 2 to 6, I see 2 triangles and a rectangle. So I know the rectangle is 4 by 2. So that's 8. So again, I'm going from 2 to 6 plus the 2 triangles. So half the base times the height. So that's 1 times 1. And then the other one is the same size, right? Half the base times the height's like a little bigger, right? We're just going to estimate that to be the same. So approximately it's 10. That would be a little bit more than 10, maybe 10.4, 10.3, just a little more. And then what does that mean, right? Is that the next one? Oh, using a midpoint Riemann sum. They didn't want me to do it that way. Let's try it again. Let's do a Riemann sum. Midpoint with 2. So the width then for a Riemann sum, top subtract bottom divided by 2. So the width is 2. And then midpoint from 2 to 6. So from 2 to 4, the mid is 3. So at 3, it's 2.2. And then the next mid goes from 4 to 6, and the middle is 5. And so at 5, it's 3. And then that would be my answer. All right, pretty close, right? So like this is a Riemann. This is what I just did by just looking at the shapes. Part C says write a sentence. What does it mean? So what are the years? From 1992 to 1996. How many births were there? There were 10.4 thousand or 10,400 births because it's in thousands. So it's no longer a rate when you integrate. Part D, use the information to approximate the derivative at 5. So to approximate the derivative, it's slope. So if I want to know what the derivative at 5 is, I'm going to go and find the slope that's around 5. So I'm going to go 3.5 take away 2. And then in the bottom of 6, take away 4. And then you don't have to reduce it down. All good. That would be the rate. And that would be births per year, but it'd be births per year squared, right? In terms of what it would look like. So they're looking for that. All right. Next, part E. Write a sentence telling what your answer in part D represents, meaning using correct phrases. So, what that means is 5, first of all, is what? So what year is that? 5 plus 1995? The birth rate was increasing. At that rate. That's what it means. If that was a negative number, then the birth rate would be decreasing during that time. Per year, per year. Okay. Number 10. Two left. Let's see if we can do this again. The graph at the right represents the density of hikers on a trail. So here you have a table. Tell what point A represents. So at point A, we have 3 miles from a trailhead. So at 3 miles from the trailhead, what's happening? Well, the answer is the density of hikers is, and it would be, 30 hikers per mile. That tells you how busy the trail is at that spot. 30 hikers per mile. All right, part B. If you integrate from 0 to 5, the answer is 110. And it says, write a sentence with numbers and units saying, what does this represent? So, 0 to 5 means from the trailhead to 5 miles away from the trailhead. How many hikers are there? There are 110 hikers. So it's no longer a rate when you integrate. From right at the trailhead to 5 miles out, how many hikers are there in total? 110. Oh, it's a 3. I can't read. Sorry. From trailhead to 3 miles out away, it's 110 hikers. Part C. See if I can read this. The derivative is -6. Use local linearization to approximate the density of hikers at 3.1 miles. So we're going to make a line. So we need to know x, y, and the slope. Well, the slope is -6. And then at 3, we're given a point. So at 3, the point is 30 from the table. So it would be negative 6, x minus 3 plus 30. And then to approximate at 3.1, we would just plug that in. And that would be the approximation there. Write an integral expression for the total number of hikers on the first 6 miles of this thing. So to integrate the total number of hikers from 0 to 6, this integral from 0 to 6 of the rate would tell me how many hikers there are. Then it says use a trapezoidal rule. Keep bending my head over here. See if this works better. Use a trapezoidal rule with 6 subdivisions. So we're going to go top subtract. For the width, it's top subtract bottom divided by 6. So the width is 1. So we're going to approximate this up here. So it's this D and E together. So it's 1/2 times the width. And then the first height plus double the next height. And this is from the table. Plus double the next height. Plus double the next height. And the next height. And the next height. And then don't double the first one or the last one, just using the numbers in the table. Use your answer to part E to approximate the average density. So if I would calculate that, all of that whole number would be 180. The average density, again, is an integration question. It goes from 0 to 6. This is the calculus formula for it. We already did this part, so you integrate from 0 to 6 and divide by the difference of the bounds. We already did that, so it's just 180 divided by 6, and that equals 30 hikers. So on average, there are 30 hikers per mile over the whole trail over those 6 miles, and that's the average number of hikers per mile. All right, last one, number 11. The graph at the right models acceleration. And then you have this. So this is not velocity, this is acceleration. It says, what is the acceleration at 2? So at 2, we need an equation of this line. So an equation of that line, the slope, so it goes up 10 and over 3. That's the slope. I'm using t because this is t, so it's t minus any number will do. So you can use 3 and 10 if you want. So the point 3, 10, and then you would plug in 2 into that. And that's good. And that's feet per second squared. You don't have to simplify it unless you wanted to. So you find the equational line and then plug in 2, and then you don't have to simplify it. When is the acceleration 10? And that's between 3 and 4. Part C. What is the minimum acceleration? And so that would be the lowest number there, negative 5. So on the graph, it's negative 5 secant squared. Second squared, that's the lowest point, the y value, negative 5. D, if the initial velocity is 0, what is the velocity at 6? So the starting value is that. I integrate the acceleration from 0 to 6. And that would give me the answer. So I need to find the area from 0 to 6. So that's a trapezoid. That's 1/2. The height of the trapezoid is 10. The two bases are 1 and 6. That's 7. So 70 divided by 2. So the answer is 35. That's the velocity so this is the velocity at 6. If the initial velocity is 20 feet per second, how would that change? So now it would be 20 plus what we just said, which is 35. You don't have to write it again, plus 35. So now it would be 55. And then it says, hey, how about if the initial velocity is 20, but now we're going to 7. So the initial is 20, but now we're going to 7. So now we have to integrate to 7 to figure out what that is. So we already know 35. 7 is a triangle, but it's below, it's negative. So half the base times the height, and we don't have to simplify it, just to get into that habit. So we have a little triangle there, half the base times the height, but it's negative. That's what the value would be there at 7. That's it. Mr. G Math over and out. Great job reviewing with me. Until next time.